Okay.
Cool. Okay. I guess I'll start. We're a couple of minutes early, but that's fine, I assume.
Yep, I'm fine with that.
Yep, cool.
Just talk a little bit longer.
Yeah. Okay, so hi. Thank you very much for inviting me. I had great plans to do lots of research in multimodal work, but that didn't quite happen. I'm actually going to talk a little bit historically, but what I'm going to talk about is about how you transition computer vision systems from research into the real world. And I'll use lots of historical examples from my career, but I think it's still relevant today. I think even though we have a large number of computer vision systems that are really working in the real world, I think not many people understand what you need to do to transition there. And even up to quite recently, we found we're learning a lot in this domain. So that's what the subject is here, making stuff work in the real world. As Bodo said, so I lead now the All Data AI group at Microsoft Cambridge. So what does All Data AI mean? Well, the acronym is ADA, and you may have heard of Ada Lovelace as the first computer programmer. And we can discuss Babbage Lovelace contributions to the early computation, but something that she did very definitely observe in 1840, so nearly 200 years ago, is that computers, or the concept of computation then, was really about calculate, what we would call today a calculator. And specifically, it was mainly about how to get bombs to fall efficiently on your enemies by calculating missile trajectories. That's what people really dreamt of. What Ada Lovelace observed was that the difference engine might act on other things beside numbers. And she gave examples of music. And she probably had in mind vision and understanding documents. So what we do in our research group is very much look at the areas of AI that deal with complicated data structures, complex real-world data structures. I call it big data, small data, and funny-shaped data. In terms of technologies, we do things like graph neural networks. We look at Bayesian deep learning. So when you're lacking data, so the small data scenario, which I claim is actually very, very common, lots and lots of real world examples, you actually don't have lots of labeled data. So that's something we're very interested in. And something we do a lot on is machine learning on programming languages. So if you were to look at my recent publication list, you would find actually most of it is in programming language, or not most, I run a large research group, so I don't do a lot of publication every year, but where we are publishing is in the area of programming languages. And that's partly because I'm really interested in how we can design new programming languages for AI and machine learning. I still do some computer vision, but my main focus is programming languages. Before I came to this research group, I worked on something which you may have heard of called the HoloLens. So if anyone's unmuted, can you see any sort of pointer? Does my mouse pointer transmit?
Yes.
Yes, it does. Great, thank you. Yeah, and the video is without sound. That's intentional. So the HoloLens is a device being worn by Julia Schwartz here. Julia Schwartz is an amazing designer and engineer. So she's the person who understands the computer vision. So she was designing these user interfaces. And what's happening here, and sorry, I spoke over the start of the video, we don't see it. The HoloLens device has a Kinect-like camera in it. It is tracking her hands, providing full 30 DOF, 30 degrees of freedom tracking for each hand. And she's here showing the HoloLens user interface that she designed and built based on our hand tracker. And I'm going to lead up to how we got that hand tracker to work in this device, which is about 100 times less compute than an iPhone 7. Right, so this device, the device has compute twice of a large iPhone, but for us, for hand tracking, we have basically the amount of an Apple Watch, or 1/100th of an iPhone 7. So how do we make state-of-the-art hand tracking run on an iPhone 7? Before I do that, I'm going to do a very quick sort of historical run through computer vision problems that I've been involved in, and in particular how we turn them into products, or how we turn them into something reliable enough for people to work on. So as Bodo said in 1996, he correctly said, I finished my PhD in 97, but I went to get a job as a postdoc in Oxford in 96. Let me recommend to anybody listening, it's a very bad idea to get a job as a postdoc before you finish your PhD. It's very difficult to get two jobs done at once, so try to finish your PhD before you go anywhere. So I went to Oxford, working with Andrew Zisserman and in Mike Brady's group. And our idea was, well, robots would need vision to navigate the environment. So, could we take a video sequence like this and somehow recover a structure and motion, or simultaneous location and mapping? Could we recover the blue camera trajectory and maybe some representation of the 3D structure represented by the red dots here? Could we figure that out? For those of you, I'm sure most of you know, but I think it's fun to see the inspiration of classical computer vision then. This amount of data, even in 1996, was an enormous amount of data, megabytes per frame. So, and the tools we had there were pre-deep learning. So the tools we had essentially were mathematics. So how do I turn a complicated image like this into mathematics? Well, we used tools from the 70s. So in the 70s, psychologists were trying to simplify or understand human vision. And Jitendra will almost certainly show these same videos later. The two of us started using them about 2 years ago in our talks. I claim simultaneous invention. The psychologists were trying to find out what's the simplest signal that I can have to sort of understand motion in the scene. So here we can see the person with the rotating wheel. On the rotating wheel, there were some illuminated dots, and those dots alone serve to give you some representation of what's happening. But I'm not sure you definitely say, oh, that's a rotating wheel. What's interesting is when you attach the dots to an object that we know well. So you may think maybe this is a standing human, but when we play the video, it becomes, I would say, blindingly obvious that this is a walking human, even though we've reduced the entire motion to a tiny number of dots attached to the human. You might not know what this is before I hit play, but once we do hit play, then I think you form a very strong percept of what's happening. It's a human. You can do tests and show that people are actually pretty good at estimating the gender of the people in these videos, even though there's only a tiny number of dots, and they can do activity recognition from this data. So I think you probably have a hypothesis that this is a person who walked in, climbed a ladder and started painting. Maybe you have an idea what this person is doing. I don't know how you're dealing with lockdown at the moment, but I think a lot of us are doing this sort of exercise, or at least during dense lockdown, people were doing this sort of exercise rather than running and cycling. So from this tiny amount of information, there's lots more of these. You can find them on the internet. We can determine what's happening in a video sequence very easily. And of course, the trick used from structure and motion is, well, if I could turn each frame of my video into something like that, then I would have a mathematical problem, not a sort of nasty visual recognition problem. I would just do some stuff with these 2D trajectories. So we knew all that, and that's what we were trying to do back then. And we could not make it work, right? So 96, there was no way we could deal with this amount of data. There was no way we could get decent structure and motion from this data. So what did we do? We did strategy number one that Zisserman said to me at the time, why don't we do it for something simpler? Do it for turntables. And we can do special mathematics, right? That deals only with the rotating case. And I was like, Andrew, no, that's pointless. Like, we're not going to learn anything. It's never going to be useful. Why make the problem easier? It was a brilliant idea, as all Zisserman's ideas are, obviously. So the idea was we're going to just look at turntables. And if you just look at turntables and you apply the same trick, track the 2D points, now it turns out you get super accurate structure of motion. So we have 10 milliradians of accuracy in the angle estimation for these cameras. We got nice 3D points. Everything worked beautifully. We could go further. We could now use the beautiful cameras, and because we had a blue screen background, we could get nice 3D models. And even today at CVPR, we're looking at 3D as somehow an area of computer vision where we like doing 3D because you kind of know you got it right. One of the things we were proud of then, and I'm still proud of now, is that we went to sort of great effort. We engineered the hell out of it, as I say, to build a system that was really robust, got nice 3D models. We went sub-pixel in our edge detection here, which meant that each input image is only, you can see the pixels here. I don't know, this is maybe 30 pixels high. And this 3D model derived from this sequence is maybe 1,000 polygons high in this direction. So we were able to get super fantastic super resolution, 3D super resolution from 36 low-res input images. So this is 99. I said 96, so 99 by the time we got this working. And we thought, this is brilliant, right? We've got a 3D modeling system, and because it's on this turntable, we can actually believe in it. Remember, 20 years ago, computer vision didn't work. So it was a very unusual situation. We actually thought we could make this work. So we made a startup, and this was almost a disaster. So why did we think we could make a startup? And this applies today. You will have algorithms or results where you think, great, I've done something novel. And what we did there was novel, which was, although the object was on a turntable, we had no other information about the video. So everything was recovered purely from the images in an uncalibrated manner. It was definitely cool. Even today, people love 3D models. And most importantly, we could see a way to make a reliable product using this technology. It turns out, despite being novel, cool, and workable, it was also entirely useless. And why was it useless? It was useless because the kind of industries we were trying to sell it to were very special industries. The only people who cared about 3D modeling were special in that they were the car industry or the movie industry. So, but let's first of all look at those advantages from a research point of view. We were really excited that we needed no calibration. We had already said you needed a turntable and a blue screen. So once you've got a turntable, you may as well drive it with a motor. And once you're driving it with a motor, it's harder to make it unequal angle than it is to make it equal. So really, the system that you could have built from this had zero of the research advances that we made were relevant at all for the system. You'd be far better off just engineering a system with a blue screen and a motor-driven turntable and calibration grids and all of that. So it was just a stupid idea. We tried, anyway, we didn't know it was a stupid idea. So we went around to lots of movie studios. We weren't that interested in auto industries because, I don't know, we weren't car people, we were movie people. So we went to lots of movie studios and everyone said, yeah, lovely work, really nice, useless, don't care, don't want to buy it. Somebody said, oh, this picture, what are these? And we explained those are the cameras. And it's like, how do you get the camera position from those videos? And we explained structure and motion. You have to simultaneously recover the 3D points and the camera position, otherwise it doesn't work. So it turned out that the movie people really, really wanted the cameras. Why did they want the cameras? They wanted the cameras because they wanted to take video like this one and stick 3D objects into it. If I flash forward for a bit beyond how it works, I'll show you what they wanted to do. What they wanted to do was they had the idea of maybe they would have children in a school like this one, and maybe they would have 3D virtual candles in the air above them. That was what they wanted to do. But of course, we didn't know that. We thought they just wanted 3D models. So if I go back to my 3D models. Oops. So what do we do? So we went back, and this time we had to take on the hard problem, right? We had carved out a nice, easy problem for ourselves. This time we had to do it for real. So we went back to the problem that we first tried to solve. This is the program we built, just showing it running. So feature point detection, feature point tracking, classic computer vision. Each of those feature trajectories corresponds to a 3D point. So using ransack algorithms and so on, then we can build this representation, which is a 3D point cloud and a moving camera, which is sort of simultaneously recovered. Of course, this point cloud is horrible. So when we thought we were going to be selling a 3D modeling tool, we were kind of throwing our hands in the air because this point cloud was so horrible. But it's just enough. If you look here, right, you can see a kind of an L-shaped 3D structure here. And that is just enough, if you remember the original sequence, to identify the wall of one of the buildings. And then what I'm going to do is select the 3D points on the wall. That's now this collection of 3D points. And now I can stick a 3D object onto the plane defined by those points. None of this stage is automatic. Right? It's fully automatic to get up to the 3D points. And now, of course, we wrote loads of code to automatically find the planes in the scene and automatically try to build 3D models. Pointless. The users are much happier indicating what they want to stick the object on by just drag selecting the scene. So here this user has put on a little ladybird. That's our kind of test case. And what we're trying to do is now, oops, this is intentional, but I was going to do it earlier, is play the video. And what we want to do is check that the ladybird appears to be stuck correctly to the scene. And I think you'd agree that it looks as if, aside from its blueness and its bad lighting, that the ladybird is well stuck to the screen. Now, even then, late 90s, people said, well, that's pointless because you just explained to me, Andrew, that these people don't mind, these people, the movie industry, don't mind manual labor. In fact, there's, even today, there are teams of sort of young interns in basements in Los Angeles and London, manually marking up frames of movie in order to achieve special effects. And you might say, well, couldn't you just stick the ladybird in position every 2 frames or every 10 frames? And then, it would be fine. You could interpolate between them. Well, it's interesting to see actually how much the ladybird has to move. So when I have the background switched on, you can notice the camera jumping around, but you don't realize that the thing is moving tens of pixels in every frame because your visual system will stabilize the ladybird to the background. So when I turn off the background here, you can see that in fact there's an awful lot of movement of the ladybird from frame to frame. So it wasn't possible to do it manually. It was lucky. We actually saved quite a bit of money for the movie industry and got awards and everything. Let me talk a little bit about how you do this. So, we're used in computer vision to, there is a benchmark data set, and it is valuable to the community to collect a benchmark data set. So then, our benchmark data set wasn't enormous. We gathered 100 test videos, just by walking around Oxford and generally getting videos. We built metrics on those videos, and just as we can do today, just as we overfit on data sets today, we easily overfitted to these metrics. Before we did that, first of all, because we're building something for real and because we weren't caring about the publication, all we did was read every single paper and implemented every known algorithm. So sometimes I see people responding today saying, a reviewer may say, why didn't you compare to algorithm X? And our tendency today is to say, oh, well, algorithm X is commercial or the source code isn't available, so I don't need to compare to it. When you're selling, there's not a question of whether you need to compare to it or not. You have to compare to it, right? You have to be as good as the competitor. So there's extra work there. But the other thing you notice after a while, once you've implemented 5 algorithms from the literature, implementing number 6 is incredibly much easier. Once you've implemented 20, implementing number 21 is incredibly easy. So we really did just implement everything known at the time. Yes, we had secret sauce. Yes, we had stuff that we were really proud of in there, but it kind of doesn't matter, right? The point is we made it work. The other thing we do a lot was break our metrics. So we would have some metric like number of inliers or number of points with error less than 0.2. Any metric like that, the system, it will break it. It's like you will overfit. So what it did when we had lots of, our metric was number of points, within 0.2 pixels. The system would take the hit of losing all the points every 20 frames. So it would score a massive error every 20 frames, but the RMS over the sequence was kept low by that. And it only had to do short range optimizations. So we had to change our metrics because even without us trying, we weren't trying to cheat or anything. We were just trying to make the system as good as we could. Optimizing on metrics gave us bad brokenness and we had to change the metrics. And then, of course, after a while, we got 100% on our test set on videos that we cared about, having fixed the broken metrics. So then we got 100 new videos, threw away our old test set. And of course, our success rate was down to 50% again. So even though we had gone really good on our training set and we thought it was representative, this is something I like to say when you're trying to sell something. This is not Kaggle, this is the real world. When you're building something to ship in the real world, you don't have access to the test set. The test set is going to come after you ship, right? When it gets in the hands of customers. So everything you're doing is on the training set. You better make sure that you are not overfitting to your training set. You better make sure that you're keeping 80% of it away for very occasional testing. So it's nice not to be in sort of that kind of competition, but of course you're in competition with your competitors. That's why they're called competitors. We got to use it on, this is one of the early films that we got to use it on. This does have sound, but it's terrible. Oh, it's Troy. It's they're
coming for me.
Lots of wooden ships.
The wind is bringing them closer.
Lots of wooden actors.
This will be the greatest war the world has ever seen. We need the greatest warrior.
Apparently, it's a really good film. I've never been able to sit through it. It's the acting is so terrible. So that's what you see on film. This is what was shot. There's a single boat moving on moving water. Those green dots are not there in the world. Those are our debug output that we're using just to check if we're getting anywhere. So we got one boat moving on the water, another boat behind it, and a convenient boat placed almost collinearly with these two boats, which didn't help us. So that was, a nice hard sequence, much harder than we dealt with before, which we were able to do for that film. Of course, it got used in this clip that I showed you earlier, which is what my child is most interested in. And it was most useful for television. So we never got an Oscar. I'm very sad about not getting an Oscar. But we got something called an Emmy, which I explained to my mother. I'm Irish. My mother's Irish. I explain an Emmy is a thing that isn't an Oscar. That's a good definition of an Emmy. So that technology comes forward then decades later to the HoloLens device that I showed you at the start. So the same core ideas, although I did not work on the head tracking for the HoloLens, it was George Klein, and one of the most beautiful pieces of engineering I've ever had the privilege of observing. So the HoloLens, as I said, is a single device, total compute power, about the size of a high-end mobile phone or a mid-range laptop. On that device, 4 grayscale tracking cameras, a Kinect style depth camera, and an RGB camera. Apologies if I'm pointing to the wrong one. I think no, there's the depth camera, there's the RGB camera. And that device takes a video view of the world through the 4 cameras, where again, in real time, battery powered, tiny amount of compute. It's applying the same sort of technologies. And this is shipped, a few years ago, we shipped Connect V1, we now ship Connect V2. And a beautiful piece of engineering here in making all of that run in, thousands of times less compute than we had available even in '96. So for me, having done, the sort of structure of motion work and got that working, I want to say another story about shipping something. I'll talk about shipping, body tracking, and Connect. And this is going to be a story of how I was working on exactly the wrong thing and my colleagues were working on the right thing. But we still had some innovations that we made that were valuable to shipping. So I moved to Microsoft 2004, 2005. And in Microsoft around then, there were people like Jamie Schotten, John Wynn, Carsten Rota, Antonio Cremonesi, who were working on this stuff that I'd never really thought about before, which was, could you take every pixel of an image and could you label every pixel in the image with the category label, the semantic segmentation label? I will try and turn off the sound here. Maybe I'll just sort of randomly scrub through the video. So again, 2004, they have a real-time system that can do semantic segmentation on on camcorder video coming in through the boat. Amazing piece of technology based then on decision trees. Now you would use something more accurate, more efficient. We'll see. I was interested in working on something else. I wanted to work on a scene where the motion was more complicated than we had done from structure of motion. Structure motion is actually pretty simple, right? There's 6 degrees of freedom: camera, X, Y, Z, and camera orientation, 3 DOF, maybe focal length, so maybe 7 degrees of freedom. And the structure motion problem works essentially in this world of no motion, other than that caused by the camera. So it's a rigid world. So I was interested in, could we do something to track motion of the human body? And you know, state of the art around then, this is ICCV 2007. State of the art around then is we could take an object, do the silhouette, and you know, this paper was, which I'm proud of, very proud of, was about generating multiple hypotheses of from the silhouette, frame by frame, and then piecing together those results to give you a tracked 3D human body. So it was a good system. It kind of only worked on sequences quite like this one, and it was 1 minute per frame. So around then, Xbox people came to us, and they had this vision, and basically their vision looks like you know, what you see here. They had this idea that they would stick a camera in front of the television, and then the camera would follow human motion, and people would jump up and down and, you know, play in front of the camera, and it would be amazing. It was a sort of an interesting moment, because as I was the person working on body tracking at Microsoft at the time, I said, it's lucky you pay me a lot of money to work on body tracking, because I can tell you that what you're proposing is impossible. Please don't try to do it. So that was my advice, and I thought I'd save the company a lot of money by not trying to do something as foolish as Kinect. And why did I say it wasn't going to work? Well, they wanted it to be much better than the computer vision state of the art in terms of motion ability. It needed to run on 10% of an Xbox 360, and an Xbox 360 is a machine is a PC that was designed in 2003. So it needed to run in 10% of a 2003 era machine, and it was really important that it could track 2 people at the same time, which we knew was doubling the number of degrees of freedom in the problem. So it was like, look, no problem. I'm a serious computer vision researcher. I can tell you this is a foolish endeavor. They said, oh, but we've got this new 3D camera. And I was like, yeah, okay, new 3D camera. It does make it a bit easier, but I'm still telling you this is like impossible. And then they said, oh, it's funny you tell me it's impossible, because we've got this young programmer in Xbox. So this is someone who was not a computer vision PhD student. This is someone who just kind of thought about the problem and said, well, why don't I make some like 3D model of the person, you know, with some polyhedra, and then maybe if I like, you know, go into the T pose at the start of the game, and then I update my model every frame, 30 frames a second, you know, maybe that'll work. So this was quite a good moment, because quite a good embarrassing moment for computer vision expert who's loudly claimed this is impossible, to be shown that you know, a couple of Xbox engineers, now admittedly Xbox engineers are genius programmers, but to show that a couple of Xbox engineers could make this thing work. Now, of course, you probably know why something like this isn't going to work, right? The difficulty is, yes, if you get into the T-pose, it'll track beautifully, but you know that after a while, it's not going to track. Something's going to go wrong. It's going to collapse. And the problem that they had was, yes, it worked great, but after, I don't know, 10 seconds, some amount of time, the system would collapse, and there was no way to recover other than design games which have 10 minutes of gentle motion followed by getting back in a T-pose, which, you know, wasn't a realistic prospect. So what happened? So, and this is, I think, the fun bit. I was the person working on body tracking. None of my work was helpful here, right? Because of the way we were trying to do it just wasn't thoughtful. Jamie Shotton, my colleague, was working on semantic segmentation using random forests. So Jamie essentially thought, how can I turn this 3D computer vision problem into a semantic segmentation problem? So he had the idea of taking the input image and then inferring, dividing the human body into 32 different segments, inferring the body parts. And the trick was that the semantic segmentation can distinguish the left hand and the right hand, even when they're both out on the left-hand side of the image. So we trained using machine learning, a system which could segment the 3D image. And of course, once it's segmented, it's pretty easy then to just compute centroids of the segmented regions. And now we have beautiful joint positions from which we get connect body tracking. How did we generate training data for the semantic segmentation? We couldn't even get humans to label these images because, of course, humans would disagree. They'd be fine about what's a left hand and what's a left hand and what's a right hand, but they would totally disagree about where the middle of the body is or what, how much knee there is. So obviously, we're going to use computer graphics, which again then wasn't really possible to use computer graphics as training data, but because it was a depth camera, it allowed us to use computer graphic training data. And then, of course, the big innovation that we made in those days, which was another reason that we knew the Xbox people were serious, was so they came to us and they showed us this, dancing thing, and I said, "Oh, all right, fine, yes, brilliant, that's really good, you can do it." We still don't know how to make it work, reliably frame after frame. Then Jamie had that idea, and then we went back to them and said, "Okay, fine, we think we can make it, but you're going to need to take your camera around the world to 10 different houses and video people in their living rooms long before we tell you we can do it, right? Long before we solve this problem, you're going to have to video people in their living rooms." We knew they were horrifyingly serious when they phoned us from some living room in somewhere in Germany or Japan, asking, something like, "Do you want the camera portrait or landscape? Do you want it, at the back of the room or top of the TV or the bottom?" The second time we asked them for lots of money was we said, "Okay, we've got this idea for training data, but basically you're going to have to get a Hollywood studio to render us 1 million frames of training data because they've got the computer graphics experts. We can't do it in-house. It's going to cost you like $1 million." So of course, Xbox people said, "Okay, fine, we're going to spend $1 million. How do you want to do it?" And I love this video we made around the time. So they designed a huge range of people of different shapes and sizes. They went to a motion capture studio to get realistic poses of people playing these games. This is just one view of the training data, where if we put all the heavier people in one space and the lighter people in another, then we can spell out connect. But I think it was the first time when we really thought, okay, 1 million training images is a good number. We know we can make progress then. Something else I want to mention just around here. For Connect V1, we were incredibly careful to test the system on a large range of skin colors. So sometimes today we talk about bias in AI, and we sometimes want mathematical techniques to remove bias, but actually the most important tool in removing bias from an AI system is in here. Right, in your brain. The most important tool is to think about how bias might occur in the system. And the most important tool is to test it on a range of skin colors. So we were specifically, for example, looking for very dark skin, very shiny skin, also very matte skin. We were just trying to think of different ways in which human skin could confuse the camera. And that was super helpful in Connect V1. And Connect V1 did not have, did not have any racial bias difficulties. We did have skin color bias in V2 when we introduced face recognition. And of course, nowadays, face recognition is one of the main areas where we focus on bias. The reason we had some difficulties with face recognition in V2 was just we thought we had solved the problem in V1. We didn't go back and check we'd solved it again in V2, and that was just something. So Connect was good. Connect sold very well. It was fastest selling consumer device on record. But as you probably know today, it's not played very much. Although again, lockdown story, we are really enjoying playing Connect at home. It's another good way to get exercise. So if you've got an Xbox 360 and a Connect, I recommend you dust it off and play Connect Sports or Connect Adventures. It's a lot of fun. And this story is relevant again today because just now, or just recently, we've noticed that. I always think it's funny. If you think about Connect V1, it was released. Xbox peripherals have incredibly careful encryption on them, so that you can't make a fake controller, which gives you an unfair advantage in a game. It turned out that you know, essentially took the decision not to encrypt the connect depth channel. So in principle, you could cheat a connect game by sending rendered depth images down the line and, you know, fooling the Xbox. But people don't want to cheat at a connect game because the reason you do it is for fun, for exercise, for sport. But of course, the decision not to encrypt the camera meant that, you know, as we know, suddenly connects were everywhere, computer vision and robotics. And when it looked like the product was discontinued, connects were selling for higher and higher prices on eBay. So I'm really pleased now that we've released this new Azure Connect development kit, which is a beautiful new camera, much better than the Connect V2 camera, really compact and just useful for lots and lots of stuff. So I'm hoping you're all those of you building real world systems or real world systems that need to work are enjoying this camera. And again, just to sort of reiterate the key story of making this product work, you don't always get the innovations where you think you're going to get them. So I was the person working on body tracking, and yet my algorithms played no part. The only part I played was obtaining training data or working on training data. Jamie was working on semantic segmentation of farm animals, not because Microsoft was going to get into the farm business, just because it was a hard problem, right? Semantic segmentation was a hard problem in 2006. It still is. And that work was what turned out to be key. So you always have this blue skies research, which suddenly turns into practice. The key then that, what Jamie was phenomenal was actually following it up and making it really work in the real world with just lots and lots of testing and lots of training data. Is that a question there? Okay, sound is there. Good. All right, final part of this is how did we end up working on hand tracking for HoloLens 2? So I just realized this today as I was looking at this deck. I'd been working on human body tracking, and it turned out not to be useful for Connect. It was useful for other reasons, right? It taught me about machine learning and, taught me about integrating model fitting and machine learning. Jamie was working on animals, so maybe I decided to work on animals. Actually, I didn't. What I wanted to do was work on something that was harder than tracking a well-known object class like humans. Right, so my idea was, humans. It's worth building depth cameras for humans. It's worth building special 3D models for humans because it's such an important object category. But wouldn't it be nice if we could just get 3D models for anything that you wanted to look at? So, for example, I just picked dolphins because they looked like not too hard, but harder than simple stuff. Why dolphins? So what do I want to do? What's the problem we want to solve here? And it's kind of a fake problem, but it's a blue skies problem. The problem is, give me some number of images of some 3D object category, right? In this case, it's dolphins, but the system doesn't know that. The system just knows there's something in common between these images that has generated these images. How can I learn or adapt a 3D model so that it explains this object category, right? So maybe I can show what I mean by showing the answer. So the answer is, what I want to do is, start with a sort of simple template of a dolphin, and then have the system automatically determine a range of modes of variation or basis shapes for the variety of dolphins. And the system should automatically give me the sliders and the slider positions for each of my training images. And we're going to do this by fitting a 3D model to the silhouettes of the dolphins. Why the silhouettes? Because all of our previous work on structure motion had depended on high contrast points. And I was bored of high contrast points. I wanted to use the silhouettes. And our idea was that maybe if you could do this, then maybe you could take a new image, like an image of the same class, but a new member of that class, and then determine the slider positions for that image, which would let you pop out a 3D drawing, right? My idea was, I don't know, maybe it would be a PowerPoint thing or a Paint 3D feature that we could have in Microsoft, and people would, pop out a 3D drawing. What were the tools we had at our disposal? Well, we had point tracking, but we didn't like point tracking because there are no points common between dolphins. Actually, that's not true. There are like 6, right? There's a few points that you can identify, tips of like the nose, tips of fins, and so on. So a very small number of 3D points. And then there's this big clue to the object shape, its silhouette, which is notoriously hard to deal with mathematically. But again, that's what we wanted to do, pop out the shape from the silhouette. So how do you do it, and how do you solve any problem like this? Well, it's probably a good idea to read some literature. So we read the books by Kundrink and by Roberto Cipolla and other people, which told us the mathematical concepts, right? The silhouette of an object is this curve out here. The silhouette is the 2D curve. I'm going to call it SI. And the 2D curve is made by a corresponding 3D curve, which lives out on the object. And what's really annoying is that if you change the camera position, if you change your viewpoint of this object, the 3D curve, the contour generator is going to move around the object. So it's kind of not a fixed 3D curve. What are we going to do to represent 3D objects? Well, we're going to use a triangle mesh, just like we do in computer games. So the object is going to be this surface M, and this surface M is going to be a mapping from a set of triangles to 3D. So what's a triangle? It's a 2D thing, and I'm going to map from triangles to 3D. And down in those triangles, I'm going to have this thing called the contour pre-image. It's like a little line drawn on the surface telling me what gave rise to the silhouette. So my point in this slide is just, you know, when there's some mathematics there, you may as well understand it, even if you're going to hit the whole thing with, you know, some deep learning regression or something later. You may, you know, even on the weekend, you might want to read about the mathematics. So, you know, we crunched some numbers, and we could build sort of okay models of things like, you know, pigeons. It worked okay on dolphins. It worked okay on pigeons. You know, we did some nonlinear optimization. It was all pretty good. It worked terribly badly on polar bears. Why? Because pigeons and dolphins, you can't see their joints. Whereas on polar bears, this isn't, on polar bears, they, you know, they have articulated components to them, right? So, and we were trying to model articulation, something with a skeleton, just with a few sliders and a linear combination of basis shapes. It worked okay on bananas. This was relevant because even then the state of the art of shape from silhouette from bananas wasn't very good. So this was a good advance. But how is it going to be useful in the real world? Well, we immediately thought this skeleton problem is a real problem. So we converted our dolphin tracker into a 3D hand tracker. What had dolphins taught us? Dolphins had taught us how to deal with 3D surfaces using a tool called subdivision surfaces. It had taught us how to very efficiently fit models to sparse data. Now, the sparse data in dolphins was silhouettes, which is hard. In the video I'm going to show you, we're using Connect data, so fitting hands to 3D data sounds easier. But it was a valuable improvement.
Physical manipulation of.
And what we were able to do is use a Connect to fit the human hand. So there's the Connect down here looking at the human hand. And we had this dream that user interfaces would be so easy to use that you would just use real world physics. And of course, we were worried about whether it would matter that you don't feel anything. There's no haptic feedback. It turns out that this, if I go back to this, just this one section, it turns out I thought it was going to be really important to make this slider really thin, so that when you grip the slider, your fingers would touch each other and you'd get a sensation of haptics. Turned out that was completely wrong. The best sensation is the one you get just at this point, not from the two-handed interaction, but when you tip the thing and it moves. And if you get to try a HoloLens too, I think it's worth, you know, really try just single finger tapping things. You get this amazing feeling as if there's a real world haptic feedback in there. So we turned dolphins didn't turn into any product, but gave us the tools to understand 3D surfaces, which we were able to use. Now, this is on a Connect V2. The algorithm that we used for it, I'll skip over that, ran on sort of 750 watts of GPU, if I remember. Now it's running, as I say, on 100th of an iPhone 7 in the HoloLens 2. And this is just showing some of the interactions that it enables. So you can pick up an object and spin it around in 3D. So how do we make accurate hand tracking on this tiny device? Well, it's the same old story, right? We're going to have to collect an awful lot of ground truth. Even if we weren't using machine learning, we would need to get ground truth for testing. But of course, our system is going to be a hybrid. The first system I showed you was pure model fitting, Buju. The second system Connect was essentially pure learning. It was random forest, not deep learning, but it was basically pure deep learning with a tiny polish up at the end. What we found is that if your model is pure geometry or pure deep learning, you do much more work trying to make it good at the things that the other one is good at. So this model for HoloLens is going to be a hybrid. We're going to use deep learning at the front end, again on a tiny device, super efficient deep learning, and then we're going to use model fitting at the back end. And that combination is going to give us our 100th of an iPhone compute. So what are we going to do to make hand tracking operate? We're going to collect some ground truth. We're going to learn about a model. We're going to use machine learning. What ground truth did we collect? We built ourselves a multi-camera rig. We got ourselves 150,000 hand poses. And again, the system hasn't been built yet. So we're asking the users, just kind of pretend you're playing with some future HoloLens. Do hand gestures that you think will be involved. And we kind of give them some idea. Maybe they're sliders. Maybe you're playing around with stuff. So we had people just play around in this custom rig that we built. You might think, oh, it's lucky you're Microsoft, you have lots of money. And yes, that's absolutely true. We can put money behind something like this in order to make it work. But also, rigs like this exist in academia. So Michael Black's lab in academia, built a fantastic human capture rig. It is possible. And it gives you such an advantage in later stages. So one of the things about this rig is that we're using tens of cameras here. We're not limiting ourselves to the small Connect that's going to be on the HoloLens headset. We got 100 different people. And of course, we remember to make sure we have a variety of skin color reflectivities and other characteristics. And also, we had manual markup. So one of the big innovations, I can't remember if it's on the next slide. No, it's not here. So if you look in this video, and maybe it's hard to see, but what we're showing here in gray is a model fitted using maximum compute, maximum everything. This is our most accurate model fitted with manual assistance to every frame. So we have ground truth for what model fitting should look like on this sequence. If you look into this sequence, you can see the green dots. That's the kind of the raw data to which we fit the model. So we made some key innovations here just in how you label the data. So how do we first label the data? Well, what we first did with the data was we thought we were very clever. We had a sort of an online model fitting. So you take the gray thing, you'd position it on the image, and then you try and use the mouse to drag the gray finger, thumb tip to near where the green data corresponding to the thumb is. Turned out doing that in 3D is kind of a pain, right? You kind of drag and then you got a different gesture like shift click to rotate, and then you drag again, then you rotate. What was much better was for us to just click roughly in the area and say thumb, index, middle, ring, pinky. So you would click, on the fingertips. But even that, we had bad user interface design, because what we had was a menu where we would say, right click here, select, is it the thumb, is it the middle finger? What was much more accurate, and this was, a good invention, was you place the mouse over the thing you want to indicate, and you use the keyboard, QWERT, to indicate whether it's little, which finger it is. So your hands never move from the keyboard on the left, your hands never move from the mouse on the right, and you never click the mouse, because when you click the mouse moves a little bit, and you miss your thing you wanted to click on. So we probably got 10x speed up in human labeling time by just really careful design of the user interface of the labeling tool, which was something we were just going to throw away after 3 weeks. But spending effort on that, saved us lots. We also needed to do synthetic training data. Synthetic training data for a time of flight camera is much more difficult to simulate. It's much more difficult to simulate than it would be for a structured light camera like the Connect V1. So we made a fully as realistic as possible visible light RGB system. You'll notice that the motions here are the same as the motions from our rig. So we use our hand models from the rig to inform the CG models, which we can now play in front of backgrounds with difficult scenes like bright light coming in. We can simulate the depth camera. And of course, we can simulate machine learning ground truth. We can simulate lots of data capture to get the 3D models, and then the 3D models go back into the synthetic system to generate machine learning ground truth. And again, you will have seen there the little semantic segmentation labeling that, again, we're using same sort of technology as was used in Connect. Finally, I said we needed to make it fast, and boy, do we need to make it fast, right? So when we that we were making it fast on, we have 2 cores, each running at 500 megahertz, not gigahertz or anything like that, and each core has 128 kilobytes of RAM. And we needed to optimize the code on this. I won't go into masses of detail, but basically say we didn't write the assembly language, but we wrote the C++ and then observed the assembly language cycle by cycle. We went to floptable. Sometimes people will tell you that if your machine is, I think this is 4 megaflops, I think, this machine. People will tell you, oh, that's what the manufacturer bills it at, but it's impossible to achieve that throughput. No, you can achieve that throughput. You just need to write your code very, very carefully and be very careful about how the assembly language is generated. There is no PyTorch TensorFlow in here because, you know, we can't have a runtime interpreter. And because our matrices are not huge, right? We've only got 4 megaflops to play with. malloc is done on the whiteboard. So if you want memory, you go into the next office and you ask somebody for some memory and they have to lose something from there. We tried simplifying our models and yeah, we've had some nice results on that, where if we go back down to polygon model from subdivision surface, it's a disaster. So here we are. Over a couple of years, we sped up our code by a factor of about 250. And that was already, you know, the world's fastest code. And as we do that, we move, you know, it's really important that as you make your code faster, so down here, down is faster, you're sometimes going to make it less accurate. So you have to then make it faster, get the accuracy back. That was a lot of fun. All of which leads us to this video
now, not only
of Julia showing us the first public launch. This was in February, of the hand tracker. This was an early release, very glitchy. But look, this is the 3D hand model that she's viewing in this battery-powered device, powered by our algorithms. So we were super excited and proud of that. So to conclude, you know, I've talked about commercializing various types of computer vision algorithm, moving from, you know, classic geometry in the 90s up to hybrid geometry deep learning today. I'm going to hypothesize that a lot of algorithms that need to run in low compute, and remember, low compute isn't just on the HoloLens, right? If you're Microsoft or Google and you're selling you know, sort of an email autocorrect or auto prediction or an email sorting system, every time you run, you know, a trillion parameter model on a user's email, you're spending real dollars. So I'm sort of obsessed with efficient modeling and machine learning, but for me, big data goes with efficiency. And I'm now delighted to be leading this team of people working on, as I say, all data AI, on big data, small data, and things that are messy, things that go beyond the regular tensors of computer vision and machine learning. Thank you.
Yes, Andrew, many thanks for this beautiful presentation. I really love this historic flashback from all the old products to the really novel things, and it's really exciting to be we are living this kind of age, and we are really able to live and observe this kind of development our kids are taking, for sure. So we have time for a couple of questions. You can send the questions in the chat if you like, or you can also just raise your hand somehow and give a note if you want to raise a question. Maybe I start with a question. I really like the approach of making the transition from research to practice. And I'm wondering, how do you deal with hyperparameter optimization in a product?
Ah, exactly. Okay, good question. So this is back to my point that when you're making a product, the test data is completely unseen, right? The test data is actually, it's actually what happens to the first 10 journalists who try it, right? In some sense, you know, you're going to make this thing, you're going to ship it. It's probably going to be launched at some press event or some, you know, some big event. And if the first 10 people who try it, if it happens not to work on them, then it's pretty hard to recover, right? It's pretty disastrous. So there's a test data. The test data is not, you know, the sort of evaluation on a huge held out, huge set that we might think of. It's almost like you need to minimize worst case. So the worst case is that it happens that the first 10 people who come are incredibly tall, right? And, you know, their hands are big and it doesn't work on them. So what does that mean when you're back over in training land, right? You know, when before you release the product? What it means is this: it means that every parameter is a hyperparameter, or hyperparameters are just parameters. The way you have to set them is by careful, you could call it cross-validation, but you really hold on to a test set that you believe in, that is as hard, you make a test set that's as hard as you can make it, and you never optimize on that test set. Like, you might test once a week, or you might test only when all other metrics give you a hint that it's a good idea to test now. That's the kind of time you might test. So hyperparameters and parameters, they're all the same. You know, you might have to grid search your hyperparameters. You might have to do whatever it takes. You may well do finite different gradients to optimize, but there's always a sort of careful test set that is the thing that's super held out. I think that's an answer to your question, or maybe it's an answer to two questions related.
Yes, exactly. And I completely agree. And then you have all the other problems about imbalancedness in data, about domain transfer, and so on. And it's really hard to to be able to deal with this. And everyone has to think about what could be cases happening when people try it out and play around with it. Okay, here I see a question in the chat. Maybe Yang, you can just switch on your microphone and raise the question.
Sure. First of all, Andrew, thank you so much for sharing the mistakes and success with us. It's a very much a fun journey, and we really appreciate that. So I guess all of us learn from some failures someday, one or the other. So the question is, could you tell us what's the most important lesson that you learned from the previous failures? Thank
Wow.
you.
Yeah, so many to choose from. Failures, I mean, and lessons. Oh boy. So this is going to sound a bit silly, but you know, always assume you might be wrong. You know, really, like, and at the same time, you know, it goes with have conviction. So, you know, I've stuck with this kind of model fitting paradigm for a long time, right? But my assumption, if I were building the hand tracker for HoloLens, my hope was that every day that we'd be able to use deep learning end to end, right? And that would basically kill my entire career. Right? I don't care. I don't mind. I just want to, you know, I'm in Wikipedia now. I'll tell you, I put that there myself. I really wanted deep learning to take over, because remember, if it did, we would have saved like half the flops. In fact, if deep learning started to work, we would have thrown away all the flops that we had devoted to model fitting, and then we'd have had twice the many flops for the deep learning model. So I was really rooting for the rival technology, but of course at the same time, I was giving every piece of commitment I had to the design of the model fitting technology. And you know, I keep saying I here. I'm just like one person on a team, but you know, it's just that I'm kind of the person associated with this model fitting technology. So massive commitment to the one you do believe in, but really try and make the other one work. After a while, I began to realize that the reason a hybrid is good is model fitting is disastrous. If here's the ground truth, and I start my model exactly one finger over, it's never going to recover, right? There's a local optimum there that the model is, you know, is never going to notice that this finger over here needs to, you know. So the model fitting is disastrous for getting out of, you know, it could start only 2 centimeters away and not get into the right minimum. But at the same point, deep learning is great for getting you within a centimeter, right? Getting roughly the fingertip. but it's not going to get you the last millimeter. There's kind of, you need too much model capacity to get the last millimeter. Okay, so now I'm telling you how we didn't make a mistake, but the mistake that I think I've made earlier is to hope that the other guys are wrong. I think you've basically got to work just as hard on the other guy's stuff as on your stuff, and really, accept that you're probably wrong.
Yes, thanks for this nice answer. I also think for younger PhD students, it's always important to teach that you have to keep your whole lifetime an open mind, and you must yourself allow to make mistakes. And even if your neighbor is dealing with how to segment a cow, this is always an important piece of work. You can later make use of it. So never speak bad about the research of other people. And I think once you have this open mind, then also research will be much easier and also much more joyful.
Yeah, and if I could just comment back on that as well, I don't know if it's still true among young academics, but when I was a young academic, we were always told, oh, you have to get a thing, you have to have, pick a thing and be famous for it. And there was always this idea that you would have a feud, right? That there would be so I wrote a paper 20 years ago on the iterated closest point algorithm. And I said, I don't like the ICP algorithm. Here's an algorithm that I think works better. Be absolutely sure that when I needed to do model fitting for HoloLens, we went right back to the ICP algorithm to check if that was the thing we needed to do, in order to go fast. And we also implemented, I think our implementation was probably hundreds of times faster than the state-of-the-art ICP algorithm, because we needed to check. And in fact, the one that we've got is a little bit of a hybrid. We do actually do an ICP step after every model fitting step, but we turned off the model fitting step. Of course we did, right? We could have saved 100 megaflops, and things got worse. So again, you need to be open-minded. People think, oh, Fitzgibbon, he's got a feud against ICP. Absolutely not. It's just that most of the time it doesn't work for me. So like, not only do I think you shouldn't try and, pick one thing, but I think you definitely shouldn't be against other things. Same as you were saying, but yeah.
I also still teach ICP in my lectures. So, okay, so here's a final question from Saksham Zuri, and I think that we have to continue with the other talks. So, Saksham, do you want to raise your question?
Oh yeah, so I just wanted to ask, first of all, thank you for the amazing talk. The examples were really good. And my question is that is it more sensible to maintain a evolving test set, like in your case, so that you have a sequestered property so that you never overfit? Because even if you test on it one every week, you'll kind of end up overfitting to it at some point.
Oh yeah. I would say there's two things. Number one, like in the first example, I was talking about Bougie, where we had this test set of 100 videos. A lot of the overfitting, we could design a way without changing the test set, just because the overfitting was like some stupid metric, right? We could improve the metric, and suddenly we weren't overfitting anymore. But to be honest, I would say, our example, 100 videos, then throw them away and get a new 100 videos is just one instance of evolving test set, right? It's like, we did throw away the first 100, but of course we checked that we hadn't lost, so really it's wrong to say we threw them away, but as we now had a 200 set. So yes, evolving. And sorry, I've made an assumption. I've assumed that by sequestered, you mean kind of separate test and train.
More like unseen kind of stuff, like say you have different cameras, maybe you see something new basically, which is different modality.
I mean, Bodo mentioned domain adaptation, and your test set is of course the one closest to reality. So you might be training on synthetic data and testing on, training on synthetic data, validating on synthetic data, but you then test on real data. So there's super sequestration of one golden test set. And basically, it's a bit like I was saying about bias. You just kind of have to use your brain. You have to think to yourself, am I overfitting? And be critical.
There should probably be a mental aspect to fighting bias than just putting stuff in the model to fight it.
Yeah, exactly. Put it in, of course. Put stuff in, but really think, why would that work? Why would that? And then, of course, poke it as hard as you can with hard examples.
That's right. Thank you.
Welcome.
All right, Andrew, many thanks for this beautiful presentations. I think for the second round, people might ask you questions via email. And
Sure.
we can't clap, or will you be available? Or
We'll see. I'll see if I can get up for 7:20, but you know, I might not. It'll be Saturday morning, but I'll see if I can do it.
yeah, exactly. So, but many thanks for having you here. And yes, so maybe Paolo, can you then continue